Hello, my name is Robert Smith, and I'm with New River Community College. And today we are looking at the chirality of molecules, which is sort of a directionality imposed by the structure of the molecule and denoted in IUPAC nomenclature. So, how to determine whether a molecule is chiral or not? You would simply look at all the atoms in the molecule and identify any that have four different things that are attached to it, four different groups. So, and it's based on the idea that you can have uh, more structural isomers of the same molecule that seem to be structurally the same if you just draw it out explicitly. If you do it in three dimensions, let's say take the example where we have a carbon, and going back into the screen is a hydrogen. Coming out of the screen with this wedge is a fluorine. In the screen is a chlorine, and also in the screen, but up above, is a bromine. And you instead had a carbon, again with the hydrogen in back and the chlorine over here, but instead you had the bromine sticking out and the fluorine in the page. Those look the same. They look the same, and they, if you try to draw them out in a linear fashion, not in three dimensions, which granted these are not great representations, but if you try to draw them out in just a linear fashion, they would be the same. But if you do them in three dimensions, they are not. You cannot rotate molecule A and molecule B. You cannot rotate molecule B such that you recreate molecule A without breaking bonds. So, because if you were to rotate B such that you made it so that the fluorine was up front, then ultimately you end up with hydrogen up top and bromine in the back. If you rotated it so that, so in any way that you rotate molecule B, you will never reproduce molecule A. So those are called enantiomers. They're a specific type of isomer that are non-superimposable mirror images of each other, akin to your hands. And that's where chiral comes from. Chiral means handedness, and it's derived from the Greek. If you take your hands and face the palms in the same direction and try to overlap them, you get your thumbs facing in different directions. So this is something that occurs in is denoting of chirality, and we show that as a non-superimposable mirror image in molecules as well. So to the problem at hand, we can write out the molecules. So we can start with a CH3, a C, a CH. No, this is another C. Sorry. So this is CH. This one's a CH. And then a CH, a C, and a CH3. That's our main chain. It's a pentane. And then on carbon, let's label the carbons. 1, 2, 3, 4, and 5. So carbon 2 has a methyl group. Carbon 3 has a methyl and an ethyl group. So we're going to put the methyl up here and the ethyl down here. And then carbon 4 has 2 methyl groups. And carbon 5 is just by itself. So let's look at each of the carbons specifically. Now, carbon 1 has 3 different or 2 different things attached to it. It has a hydrogen. So there's 3 hydrogens, but they're all chemically the same. And then you have the rest of the big group. So carbon 1 is definitely not chiral. And the same goes with carbon 5. Carbon 2 has a hydrogen, a methyl group, this large group here that encompasses everything to the right of that carbon 2, and a methyl group. But that means it has 2 methyl groups on it from carbon 1 and the methyl group above. So carbon 2 is not chiral. Similarly, all these methyl groups will not be chiral, and neither will the ethyl groups. Now we can look at carbon. Let's jump to carbon 4. Carbon 4 has 3 methyl groups on it from the methyl here, here, and then carbon 5, and then has the rest of the molecule. So carbon 4 is not chiral. Carbon 3 has above it has a methyl group, below it has an ethyl group. To the left of it, it has an ethyl group, and it's actually an isopropyl group, where it's like a propane, like 3 carbons, but it's forked. So that's called an isopropyl group. It's basically this thing right here is our isopropyl. And then over on to the right of it, it has what's called a tert-butyl. It's 4 carbons, but it's making a fork as well. So this is a tert-butyl group. So we have a methyl, an ethyl, isopropyl, and a tert-butyl group. So this one is in fact chiral. This is a chiral molecule, and we know that because carbon 3, which is right here, has 4 different things on it. So if you were to draw this out in the simplest fashion you can, so you could say carbon, and then you have a CH, you'd have a CH3 in the back, and then up front you would have, so let's see, you would have this ethyl group, CH2, CH3. And then over here, you might have an isopropyl group, which would be, it would be CH, CH3, 2. And then over above, you'd have a tert-butyl group, which would be C, and then CH3, 3. But you could also have it so that this carbon has the methyl still in the back, but instead the tert-butyl is sticking out. So you have CH3, 3 of those. Isopropyl is still where it was. And now we have the ethyl group. That shouldn't have a 2. You have that set up, and they are non-superimposable mirror images of each other.